for coming. So what I wanted to talk about today was some recent work that I've done on deep Gaussian processes. So this is going to be a talk about kind of a couple of different things. So particularly some more theoretical aspects and kind of furthering the theoretical understanding of deep Gaussian processes, and then some computational aspects. So this is joint work with my PhD student Simon Obanczyk, who's jointly supervised with Jonas Dutz, and then my PhD student Connor Osborne, who's actually just submitted his thesis a couple of weeks ago. So the outline of my talk is the following. So I wanted to start with kind of just a bit of the history and the context, what kind of deep Gaussian processes are and where they come from. Then I'll spend quite a bit of time just explaining what deep Gaussian processes are. So I'm assuming that not everybody is familiar with them and how they work. So I'll explain what they are and what the advantages are, why they are really so popular. And then I'll talk about two kind of recent research projects. One is more on the computational side and some applications in computational imaging, and then a bit about analytical properties in the end, and I'll see how much time I have there. Okay, so just to start with kind of the history, so the term deep Gaussian processes that was really introduced in this paper, which is just called deep Gaussian processes. So this was the seminal paper in 2013 from Damiano and Lawrence. So that was really the first one to formalize the methodology and use the term. I checked again this morning, and the paper now has over 1,500 citations in Google Scholar, so just over the last 10 years. It really has gotten a lot of citations, and just also searching for deep Gaussian process on Google Scholar does give you over 1,000 results just from 2023. So it's really a paper that has gotten a lot of interest, and these deep Gaussian processes are used in a lot of applications and a lot of different types of tasks because they just are very powerful. So the way that the authors introduced it, and it's probably too small to read here, but if you read the beginning of the abstract here, it does say deep GPs are a deep belief network based on Gaussian process mapping. So they do really draw the similarity to deep neural networks. And so they use, for example, the phrase architecture to describe it. And so they really kind of introduce it in a terminology that's very reminiscent of deep neural networks. In that sense, the deep neural networks and deep Gaussian processes do share similarities as well. So they kind of have in common that they define a very complex structure through iteration. So in networks, there are these different layers, and as we'll see, deep Gaussian processes have the same. And so by defining these more complex structures, they have kind of a common aim to improve the quality and the accuracy of the predictions that you can make with these models. Our interest in deep Gaussian processes comes from the ability to capture non-stationary behavior. So that's something that kind of my work has been focusing on. So if you think about kind of standard Gaussian processes, the types of functions that they could model will look something like the two samples on the left here. So this is just a Gaussian process in 2 dimensions, and I'm just plotting 2 sample paths or 2 realizations. So this is kind of the types of functions that they model. Whereas on the right-hand side, I'm plotting 2 samples of deep Gaussian processes. Again, just 2 samples in a 2-dimensional space, and you can see that they kind of fundamentally are a lot more complex and can model much more complex behavior. And that's kind of our interest, and where a lot of their power comes from, that they have this very complex behavior. So that's a bit about the history. So what are deep Gaussian processes? So deep Gaussian processes are stochastic processes. I'm going to start by defining a standard Gaussian process. So as I mentioned on the previous slide, these deep Gaussian processes are defined through iteration. And in particular, you use a lot of standard Gaussian processes, and then you kind of put them together in some way to get your deep Gaussian process. And so you really need to understand first what a standard Gaussian process is. So a standard Gaussian process I'm going to note by F. So this is now a stochastic process. The GP here means Gaussian process. To specify the distribution, we need to specify what's known as a mean function, which is this function m here, and then a covariance kernel. So it's similar to Gaussian random variables, where you just have to specify a mean and a variance. Okay. If you have not seen Gaussian processes before, I've given you the definition here in blue. So what this means is that if you look at a point ui in the input domain to your stochastic process, then f at ui will be a Gaussian random variable. Right? So you can think of this one-dimensional example that we have in the bottom right here. So we now have a function that here is a function on the domain from -3 to 3. So the input space is just one-dimensional. And then at each point, for example, at the point 0, your function f would now be a Gaussian random variable with a certain mean and variance. And in this case, I've chosen mean 0 and variance 1. Okay? So you can think of it as kind of being pointwise defined as a Gaussian random variable. All of the finite dimensional distributions are also Gaussian. So if you look at any collection of points, then these also follow a joint Gaussian distribution. The expected value comes from the mean function. So that's what the mean function specifies. In this case, here I've chosen mean 0. And then the covariance kernel k is what gives you the covariance between the different random variables. So it gives you the covariance of the Gaussian process f at a point ui and f at a point uj. Okay? But you can really just think of this as kind of a collection of Gaussian random variables at every point in the domain. You can also think of it in terms of the sample paths or realizations. So that would look something like this. So a realization of this would be a function. They still have the property of Gaussians that they kind of stay close to the mean, and then they fluctuate symmetrically around the mean. So here you can see that the functions all stay close to the chosen mean 0, and then they kind of fluctuate around the mean with a size that's proportional to the standard deviation, in this case, 1. Okay. So this is what a Gaussian process is. So you can just think of it, you can think of it as a stochastic process, or you can think of it as a probability distribution on functions. Okay. So to specify the distribution, you have to choose the mean function m. There, it's quite common to use quite simple things. So in our work, we usually just set it to 0. You can choose other things as well. So everything extends as well. But in our applications, usually just choosing 0 is sufficient. You could also choose some polynomials. And then the other thing that you have to specify is really the covariance kernel. So the covariance kernels are typical examples that are used in applications are this family of Matern covariances. So they are a parametric family where you have 3 different parameters. So you have the sigma squared, the lambda, and the nu, which enter into this general expression. So it is a parametric family. It does include some examples as specific cases. So in general, this general expression looks quite complicated. It involves the gamma function here. So this is gamma, the modified Bessel function of the second kind. That's the nu here. But in some special cases, it does simplify, and it is really used quite a lot. So it does, for example, include the exponential covariance kernel, also called the Laplace kernel, which is this example here, where you take the exponential of the norm. And it also includes the squared exponential kernel, so called the Gaussian kernel or the RBF kernel, where you have the square of the norm inside the exponential. Okay. So by looking at the expression, you can see the way that you model the covariance is really as a function of the distance. So the covariance between f at u and f at u prime, which is really what this covariance kernel is exactly equal to. That depends on how far u and u prime are apart. Right? So that makes sense if you think back to what you're actually doing. So you're modeling the covariance of f at ui and f at uj. If ui and uj are close together, then these should be very highly correlated, right? Because you have a continuous function, right? So if your UI is here, then your UI, your J is just slightly further to the right, then you have a continuous function. And so what's going on at those 2 points in the function is highly correlated, right? So on the other hand, if you have points that are very far apart, so if the UI is all the way over here at -2 and the uj is all the way at 2, then those are very far apart, and what value the function takes at those 2 points can be very different, right? So having this depend on the distance is kind of just saying that you're modeling a continuous function. So that makes sense. Okay, so that was a lot of maths. I'll show you some pictures now. So as I said, the Matern kernel has these 3 parameters. So the sigma squared is just the marginal variance. So if you look at the expression that you get when you plug in the same variable u in the Matern kernel, you can see that that just gives you sigma squared. And by definition, that is just the variance of f at that point. And so the sigma squared is really just the pointwise or the marginal variance. And then you have these other parameters, lambda and the nu. So when you change the lambda and the nu, what that changes is the length scale and the regularity. So that's what I mentioned here. So lambda is related to length scales, and the nu is related to smoothness and regularity. So here I've shown you 4 different plots. In each plot, I am showing you 5 sample paths or 5 realizations of a Gaussian process with a Matern covariance kernel, and I've changed the parameters in between the different plots. So in the top row, I've chosen the exponential covariance function. So the Laplace covariance function, this gives you sample paths that are continuous but not differentiable. So they are Hölder continuous with exponent less than 1/2, and you can see that you get something that's quite rough. Whereas in the bottom row, I've chosen the Gaussian covariance, so the RBF, or the squared exponential covariance, which gives you sample paths that are infinitely many times differentiable, and you can see that they do look a lot smoother. Changing lambda changes length scales. So in the left column, I've chosen quite a large length scale, lambda equals 1, and you can see that you get more kind of long scale fluctuations. And in the right column, I've chosen lambda equals 0.1, so much smaller length scale, and you can see that you get oscillations on much smaller length scales. So this is one reason why these family of Matern covariances is so popular. It is a parametric family, and by tuning the hyperparameters, you can really get kind of very different behaviors, and you can model very many different types of phenomena. One big drawback is that it is a stationary covariance function. So mathematically, that means that the covariance kernel only depends on the distance. It doesn't depend on u and u prime explicitly. So that's the mathematical definition. Intuitively, you can think of it as the behavior being the same everywhere in the domain, right? So if you look at these sample paths, and in the bottom left here, for example, if you look at kind of what the functions typically look like in the left hand of the domain and what they typically look like on the right hand side of the domain, that is exactly the same, right? So the behavior isn't different in different parts of the domain. And that's really something that's one of the major drawbacks of this family. So what you can do to combat this is to use deep Gaussian processes. So there are many other ways of making or modeling non-stationary behavior, but one way to do this is through deep Gaussian processes. And the way that they do this is really just through hierarchical models, right? So you can think of it in terms of kind of the iteration that I mentioned earlier, or in terms of kind of more classical statistics, it is really just a hierarchical model. Right? So then you get the types of samples that I showed you in the beginning. So here I have sample paths in 1 dimension, and you can see that what we're getting with this particular construction of the deep GPs that I've chosen to generate these plots is that in some parts you get something that's very smooth, and then in other parts you have something that's very oscillatory. right? So what I'm doing is that I'm changing the length scale lambda in parts of the domain, right? So the lambda is no longer the same everywhere. We are able to get different length scales lambda in different parts of the domain. How do we do this? So we do this through a hierarchical construction. So we now work with a sequence of stochastic processes FL. For the first process F0, we start with a standard Gaussian process. So the F0 is just a Gaussian process. For simplicity means 0, some covariance function k that we've chosen. So the F0 could just be a Gaussian process with a Matern covariance function like we've just seen. And then on the higher levels, you then do something slightly different. So there you then construct the FL plus 1 as a conditional Gaussian process. So the FL plus 1 conditioned on the FL is then a Gaussian process where the FL enters into the covariance function k. Right? So at the moment that is completely abstract. I'll give you some examples later on. But really this is then just kind of a sequence of Gaussian processes where one always depends on the previous one. So the F1 would, the distribution of F1 would depend on F0, and F0 somehow defines the covariance structure. Right? As I said, at the moment that's very abstract, and I'll tell you exactly how to do that on the next slides. Okay. And then the deep Gaussian process is just a stochastic process in this hierarchy, which has a certain number of layers. So a deep Gaussian process with L layers would have kind of L elements in this hierarchy. So that would be the FL minus 1 here, since we're starting at level 0. The object of interest is then usually the final layer, so the FL minus 1, right? So that's the one that kind of has the most complicated distribution. And the previous layers, in a way, just act as hyperparameters, right? So if you are familiar with hierarchical models, this is really just kind of specifying a prior with other hyperpriors on the hyperparameters, which are the previous layers, right? If you're not familiar with hierarchical models, you can just really think of it as this sequential construction that we have here. So how exactly do you do this? So there are many different ways and you can do it. So the original construction, which is in this Damiano and Lawrence paper, is based on composition. So this is kind of very similar to the structure that you also have in deep neural networks, right? So if you think about deep neural networks, what do? You take the output of one layer and you feed that in to the next layer as the input, right? So the output of layer L goes in as the input to layer L plus 1. So you can do exactly the same with Gaussian processes. Mathematically, that corresponds to just composition. And then you can write it in this form here, right? So can then define the FL plus 1 as a Gaussian process. It has a covariance function that's based on the Matern covariance function, but instead of just evaluating the Matern covariance function at the inputs u and u prime, we evaluate it at FL at u and FL at u prime, right? So it's really the output FL u of the previous layer that goes into the input in this layer. You of course have to make sure that kind of the input and output dimensions match. So you might have to include a transformation here. I wouldn't worry too much about that. It's really just like making sure that the input dimension of layer L plus 1 matches the output dimension of L, so that you can do the decomposition. An alternative interpretation of this, which some might be familiar with, is the idea of deformation or input warping. Right, so that's again a kind of classical tool in statistics, where you deform the input space to get non-stationarity. Right, so the way that you get non-stationarity here, so if you want, is to kind of in the original input domain, if you have 2 points u and u prime, you can either push them artificially closer together using the transformation FL. That would give you larger correlation, or you can push them further apart with FL, which would give you less correlation. And that's kind of how you can introduce this. And that's kind of where the input warping aspect comes from. Okay. As a very simple example, you can think of this function, which does exactly what I just described. So in this part of the domain, it pushes things closer together. So you have very high correlations, and so you get constant functions. Whereas on this part of the domain, it actually pushes things further apart, and so you get less correlation, and you get more oscillatory ideas. Okay. So yeah. Hopefully one of these things, either the input warping or just the composition as you do in neural networks, would make sense to you. Another example that you can do is based on this construction by Paciorek and Shervish. So this is a kind of general recipe for getting non-stationary covariance kernels. So if you do have a covariance kernel, such as the Matern kernel, which is a stationary kernel, which depends on a scalar length scale parameter lambda, what you can do is you can then choose a non-stationary length scale parameter lambda. So you're making lambda a function of u. And then you can kind of use this general recipe to build a non-stationary covariance function from there, right? So you're kind of trying to take the scalar length scale parameter lambda that you have and make it dependent on space, so that you do have different length scales lambda in different parts of the domain. So you could have one part of the domain where the lambda is large, and another part of the domain where the lambda is small. If you apply the general methodology that is in this paper, you get this covariance function here. It looks slightly strange just because you have to make sure that it still is symmetric and positive definite, but this is what comes up. In the context of deep Gaussian processes, you would then use the previous layer FL to define the length scale function of FL plus 1. So the FL plus 1 conditioned on FL is then a Gaussian process within this non-stationary covariance function where the length scale lambda is given by a function of the previous layer. So length scale is always positive, so you have to apply some transformation to the Gaussian process FL to get something that's positive, but in general, you can choose quite general functions there. Okay. So with this construction, you would then get samples like this. So here in each column, I'm showing you an independent sample of the Gaussian process. So each column shows a sample of the processes F0 to F6. So the first row would have 4 independent samples of the initial Gaussian process F0. And then the second row has 4 independent samples of F1, where this F1 corresponds to this F0, this F1 corresponds to this F0, and so on. And then we just iterate, and in the end, we have samples of F6. So you can see that the non-stationary behavior is evident from already the second layer. So the F0, you can see that that is just a kind of standard stationary Gaussian process. And then the other ones are all deep Gaussian processes with various number of layers. Okay, and you can see that this model kind of does what we wanted it to do. So you have some parts of the domain, such as in the top right corner here, where everything is very smooth and you have quite long correlation length. And then you have other parts of the domain where you get much more kind of fine scale features and have much shorter correlation lengths. And in particular, where in the domain the long correlation lengths are and where the short correlation lengths are is also random. And so that's another bonus of these deep Gaussian processes, that is kind of really very flexible in terms of how many different length scales you have, where they are in the domain, and so on. So that's what deep Gaussian processes are. They're really just defined through a hierarchy of Gaussian processes that are then combined in some way. The benefit is just that they really have these abilities to model very complex behavior, and that's why they're used a lot, and that's why they do work very well in very many different applications. Okay, so now I wanted to show you 2 examples of the things that we've been doing. So one, I wanted to show you something in applications in computational imaging. So there are many different applications where you can use deep Gaussian processes and where they would be beneficial. So things like seismology, where you're modeling earthquakes and earthquake data. Again, they would have this non-stationary behavior where everything is kind of very flat, and then the shock from the earthquake hits, and then you suddenly have these spikes. Similar in cardiology, if you think about the heartbeat, usually you see that most of the time it's very flat, and then there's the heartbeat coming in, which suddenly has kind of a lot sharper gradients and kind of fine scale features in that sense. Another application is in imaging. So if you think of reconstructing images, or just what images look like, they do have very sharp edges and then kind of patches of almost constant color where you have the different objects. And so they are kind of very non-stationary in the sense that we have discussed. Okay. So in imaging, what we want to do, if you want to write it down in abstract form, you can write it as this inverse problem. So we're going to have an observed image, which I'm going to call d-obs. That is related to a true image D through an observation operator G. What this G is depends on the application. And then you usually assume that you have some noise in the observation process as well. Right? So the eta here is observational noise that really usually comes from interference. So if you think about taking medical images or taking images in astrophysics, right? So there's just so much that's happening between the camera and the object that you're taking a photo of that there's just a lot of interference in there, and so there's always some noise. As I said, the observation operator G depends on the application, so it's what relates to the observed image to your true image. It could be the identity in the simplest setting, so then you would just be looking at removing the noise. Quite often it involves a blurring operator, right? So either the object or the camera that's taking the photo is moving, and then you get some blur. A lot of medical applications, such as X-ray, involve the radon transform or something similar to that. And I've highlighted that in red because that's what I'll be showing you in the examples. We're going to solve this in a Bayesian framework. So we're going to be looking at finding the probability density of the true image given the observed image. We do that using Bayes formula, and then we get that this is proportional to what we call the likelihood times the prior. The likelihood is determined by your observation model, right? So it's about how the d-obs is related to D. So that depends on your observation operator G and the noise eta. And then you have the prior distribution, which is really crucial for accurate reconstruction, right? So if you want to think of these two ingredients, the likelihood and the prior, the likelihood is the term that kind of makes sure that your observed image and the true image kind of match, kind of visually, you can think of it. But the prior is really the one that incorporates the structure, right? So that you want to have sharp edges. That's something that you really need to put into the prior. And so that's really what makes it an image. So for computational purposes, the image is just a matrix of intensity values or several matrices, depending on how many color channels you have. But if you just think of like a grayscale image, it's just a matrix of intensity values per pixel. Right? So it's really just kind of a two-dimensional grid, and then the pixel is just one cell in the two-dimensional grid. So it's, yeah, you can just think of it as a matrix. Deep Gaussian processes are, of course, defined in kind of continuous space. They are stochastic processes, so it's kind of infinite resolution. The pixels that you have are infinitely small, but you can just read off the finite dimensional distributions to get a prior. I can talk more about that if that's not clear. But yeah, we're going to use a deep Gaussian process as a prior for the image. Right. So these are some of the results that we have. So the image that we're reconstructing is this Sharp-Logan phantom, which is a typical test image in computational imaging. I'm first going to show you these results with a standard Gaussian process prior, and then you'll see what does and doesn't work in that context, and then I'll show you the results with the deep Gaussian process. Okay, so first I'm showing you results here for the reconstruction with a standard Gaussian process prior, and we've chosen a short length scale in the prior. And you can see visually that you can reconstruct the edges quite well, right? So you do have short length scales, and so you're able to capture the kind of sharp gradients that you have at the edges. But you can see that the background is not well reconstructed, right? So the background where you really do just have constant intensity values, that's something that the short length scale is not really able to reconstruct, and you end up just reconstructing the noise there. And you can see that in the error plot as well, that you still have a lot of errors in the background as well. You can do the same just with a long length scale instead, and there you see the opposite. So you can see that the backgrounds are reconstructed well, but the edges are quite blurry. And so because you have these long length scales in the prior, you're just not able to capture these sharp edges. And you can see that here in the error plot as well. Okay. Then you can use deep Gaussian processes. So that's what this is. So this is then the posterior mean reconstructed with a deep Gaussian process. So in that deep Gaussian process, we can have variable length scales. And so we can have a long length scale for the background and a shorter length scale for the edges. And you can see already visually that the reconstruction is good in both of those things. And you can see that from the error plot as well. And then in terms of the length scale that you infer, so this is something that you actually infer as part of the process as well, is that the inverse length scale looks like this. So it's 1 over the length scale. So you can see around the edges and around other areas where you have kind of fine scale features and sharp gradients, you get a small length scale, so a large inverse length scale. And then in the other parts, you get a larger length scale. Okay. And another benefit of this is because you're actually inferring the length scales, you can actually use this for edge detection as well. And we have done this in the paper if you're interested. So just to recap this application part to computational imaging. So some of the advantages of deep Gaussian processes in this context is that they are able to capture sharp edges, right? So they do have this kind of non-stationary feature that allows you to capture those. You don't need any prior knowledge on the location of the edges or the number of edges that you have. That is something that the deep Gaussian process picks up automatically. Because the deep Gaussian processes have a well-defined continuous limit, right? So you don't really define them on the kind of pixel space, where you first define them as a continuous function, and then you kind of downsample to get the distribution on the image space. That does mean that they are robust with increasing resolution. So some of the other well-used priors in computational imaging don't have that, so they are not robust, or they are not discretization invariant, and so that's something that's nice about the deep Gaussian process as well. The big challenge in this context is really getting efficient methods to sample from the posterior, right? So in the end, you want to learn what this posterior density is, so the density of the true image D given the observed image D obs. It's not known analytically, so you do have to use sampling methods such as Markov chain Monte Carlo methods to get it. And the challenge is that this is something that's very high dimensional, right? So the dimension here is the number of pixels that you have times the number of layers that you have in the deep Gaussian process. In terms of the number of pixels, even if you just have a very simple image that's just 128 by 128 resolution, which is a very small resolution nowadays, you're already at 10 to the 5 in terms of the dimension. And so these imaging problems very quickly become very, very high dimensional, with 10 to the 6 to 10 to the 8 unknowns. And so that's really a very large dimensional problem. They're also non-Gaussian, which makes everything more complicated if you know a bit about sampling methods. A lot of the early work focused on variational inference, so getting approximate inference methods. But there has been recent progress in doing the full Bayesian inference setup as well, so really doing sampling and targeting the true posterior rather than an approximation. And I've given you some references here, and that's particularly what we do in our paper as well. Okay. Just to give you a tiny bit more detail on what we do in our paper. So to get efficient methods, we, one, use this representation in terms of SPDEs. I'm not sure how many people will have seen this before, but I'll go through it a little bit just to give you an idea of what the algorithm does. So we use this representation of Gaussian processes that you can write a Gaussian process as a solution of a stochastic partial differential equation. So the F0 here, we define it to be the solution of this SPDE, where the W0 here is white noise. So that is, you can show that that's related to a Gaussian process with a Matern kernel. There's some slight technicalities, but you can think of the F0 as a Gaussian process with a Matern kernel. And then what we do for the F1 is we then define it as a non-stationary process where the distribution depends on F0. And the way we do that is that we define this kappa squared parameter here, which is the inverse length scale. In this context, the kappa squared is 1 over lambda squared, roughly. You can think of it like that. We define that through some function of the previous process, F0. Okay. So really here you have a model for the inverse length scale, and then kind of a non-stationary GP that depends on this inverse length scale, F0. The other trick that we use is that we use a non-centered Markov chain Monte Carlo algorithm. What does that mean? So it means that instead of sampling from the F0 and the F1, which is really the thing that you want to sample from, you actually sample from the W0 and the W1 in the algorithm. Right? Why do you do that? You do that because the W0 and W1 are white noise processes. So in particular, they are IID Gaussian. Right, so the W0 and the W1, they're both Gaussian. F0 is Gaussian, F1 is not Gaussian. The W0 and the W1 are independent, F0 and F1 are not independent. Right, so you really get rid of those problems, and that you can just work with IID Gaussians, which then means that you have access to good Markov chain Monte Carlo algorithms, such as these preconditioned Crank-Nicholson proposals, if you've heard of those. There's some technicalities. You have to think about how to actually solve these SPDEs, right? So once you sample from the W0 and W1 to then get the corresponding F0 and F1, you then have to actually solve these PDEs. That's something that's quite complicated, and our PhD student Simon really spent a lot of time doing that, and he's managed to really do a good job of kind of using all of the tricks that are out there. And you can use tools from fractional SPDEs and kind of numerical analysis to do that. And again, if people are interested, I can give a bit more detail, or you can have a look at the paper. Okay. So in the end, I wanted to talk a little bit about more kind of theoretical properties. So deep Gaussian processes haven't been around for that long, right? So they've been around for 10 years. A lot of the work that's out there does focus more on the computational side, and so understanding what they do theoretically is still something that's quite open, and people are now starting to look at. So I'm gonna briefly show you some results so you get kind of a rough idea about what kind of things we've been looking at. So in this part of the talk, I'm now going to consider regression. So kind of stepping away from the computational imaging for a bit, and we're just thinking about doing regression or prediction. So we just want to predict the output of a system at a new input based on some observed input-output data that you have. So mathematically, you can write it down like this. So we have some input values un, at which we've observed what some system or function of interest does. So we have this function f-tagger. We can observe it with or without noise. It really depends on the context. If you have real data, you usually assume that it does have noise. If this is synthetic data, then you don't assume noise, and so this epsilon could be positive, or it could be non-zero, or it could be zero, really depending on the context. If you then want to do prediction, you want to evaluate, or you want to find out what f-tagger is at a new input location u, and so that really corresponds to doing regression or interpolation. In deep Gaussian process regression, the prior that we put on the function is then a deep Gaussian process. And then we can do the same that we did before, that we can use Bayes' theorem to update the prior to a posterior. So in this case, the data that we have would be these function values y, right? So the f-tagger here is unknown. We put a deep Gaussian process prior on f-tagger. We condition that deep Gaussian process prior on this data y, and that then gives us a posterior on a deep Gaussian process posterior, which you can again use get from Bayes' theorem. Okay. I think I'm going to maybe skip this in the interest of time. Well, let me briefly go through it. So here we do have a regression example. So this is now the function f-tagger that I'm trying to reconstruct. Here it's just a standard plot, so it's a function of two variables. And this is the corresponding contour plot. So this is the function f-tagger, and then I'm assuming that I have 124 observations of this function with some noise. So I've observed this function, or this function here, just a regular grid with 1,024 points. And then from that, I want to do regression and kind of find out what the function is in all of the domain. Okay. This is a plot of the posterior means. So this is the reconstruction with a standard Gaussian process. This is the reconstruction with a deep Gaussian process with 2 layers, and these are the 2 layers. And this is a reconstruction with a deep Gaussian process with 3 layers, and these are the 3 different layers that you infer from the data. Okay. So this is the posterior mean of f2 conditioned on the data, posterior mean on f1 conditioned on the data, and the posterior mean of f0 conditioned on the data. You can already visually see that the deeper layers, or the one with more layers, is able to reconstruct the fine scale features better, right? So you can see here that these really fine scale feature parts are reconstructed a lot better. You can compute the errors as well. And you can see that by including more layers, you do reduce the error significantly. If you look at the error between the true function and then the posterior mean on the deep Gaussian process. Okay, so the kind of questions that we've been looking at is what happens when you increase n or increase L, right? So increasing n, you can see that typically leads to smaller error. N is the number of training data that you have, right? So it's the number of points at which you know what your function f is. So it makes sense that increasing n gives you a smaller error. You get more information on the function. And the other thing that you typically observe here, and more generally in deep Gaussian process papers, is that increasing the number of layers L that you have does initially give you a benefit. So it does lead to a smaller error, but to some extent, right? So there is usually a point at which increasing L typically does not give you any more benefits, right? So you can see that here. So it depends if you have a lot of data, then having 3 layers is still beneficial, whereas if you have less data here, you can already see that it kind of already stagnates up at 2 layers, and having a 3rd layer doesn't really give you a lot of benefit. So the intuition here is that larger L does give you a more flexible model. So initially, by kind of making the model more flexible, you can get a smaller error because you're able to fit more behaviors. But then eventually, kind of making the model even more complicated is just not going to improve the reconstruction. You just already have everything in there that you need, and so it does stagnate. And intuitively, it's also a bit related to having overfitting or just not enough data, right? So here you can see that if you don't have a lot of data, so if you only have 256 training points, then essentially you don't have enough data to kind of inform what this third layer should be. And so that's why you end up already seeing a bit larger errors. Okay, so I'll very quickly just go through the results. So we do have some theory on this. So we have theory on both what increasing n does, and we can show that the error goes to 0 as n tends to infinity under certain assumptions. And we do also have some theory on L, and we can actually show that the deep Gaussian process kind of has a limit as L tends to infinity, and that you kind of do converge something to something which explains the stagnation. Yeah. So as I said, I will very quickly go through this. Just want to spend another 1 or 2 minutes on this. So this is the result with the number of layers L. So the main result is really this here, that if you look at the distribution of the deep Gaussian process with L layers, that's really what this PLF0 is. So it's a deep Gaussian process with L layers. Then there is a stationary distribution pi that you can show that that distribution converges to pi geometrically, right? So there is kind of a limit which it converges to, and that's kind of where the stagnation comes from, that eventually you kind of just converge to something, and adding another layer doesn't really change what you're doing. You kind of already as flexible as you can be, and so there's not really much more added there. For the n tends to infinity part, this is one of the results, and I know it's way too complicated to understand in 1 or 2 minutes, but again, it's kind of just to give you a flavor. So we have results that show you that if you look at the true function f dagger and you reconstruct it using the posterior mean of a deep Gaussian process with L layers, then you can show that that goes to 0 as n tends to infinity. And so you kind of, as you have more and more training data available, the error does go to 0. And so that's kind of just a reassuring thing. Okay. So these are some of the open questions that I think there still are. So in addition to having these convergence guarantees, these analytical results can offer you some practical guidance on designing the deep Gaussian processes. The convergence in L kind of gives you an intuition why typically you only need a small number of layers, but there's still a lot of questions exactly how small this is. The convergence theorems in terms of the training data also give you some conditions, in particular on the kernel that you use to construct the deep Gaussian process, and again, the number of layers. And there's also some more work here, which I didn't really talk much about. But again, I'm happy to give more details if people are interested. Right, so that's really all I wanted to say. So deep Gaussian processes are really just hierarchical models that allow you to model very complex behavior. There's still a lot of open challenges, and I think it's a very exciting research area, designing efficient algorithms and also looking at the theory for this. If you're interested in our work, so I have a paper here, which is really just which is about the construction. So how do I construct deep Gaussian processes? And then the convergence analysis with the number of layers. This is our very recent preprint on the computational imaging side. And then here is the paper that we have on the analysis as n tends to infinity. Okay, so with that, I have said, I think, everything that I wanted to say. So I'm very happy to take any questions.